Thanks everyone for coming. It's nice to see you all, and it's particularly a pleasure to introduce Ryan Sanders. I think many of you have already met him, and this will be a chance to hear more about his research. One particularly special aspect of Ryan's visit is his parents are here. So apparently they came here for school, and yeah, so I didn't know that, but it's a particularly warm welcome to you guys as well. I won't embarrass you more. Maybe a little bit. Okay, so I've known Ryan now for several years. I first met him a while ago when he works with Alice Shockley at UCLA, and he's finishing his PhD this year. Very impressed with his first paper, and since then he's writing papers, and then I have to keep reading them, especially if they're so long. It's really kind of annoying. So I'm hoping that today he'll give me us a synopsis of all the great work he's been doing. So he's, as I mentioned, graduating from UCLA this year, and before then he was at University of Louisville in Kentucky. And one interesting thing I just learned about him is that he was a double major in physics and also in music. And I was pointing out that Casey has a very long background in music, as well as many other people, I believe, here. So you're not alone. Anyway, looking forward to your talk.
Awesome. Thanks, Pete. Yeah, thanks everyone for having me. I'm going to talk to you today about a large part of my thesis, so I'll try to cram as much stuff in here as I can. And in particular, I'm going to be talking about galaxy metallicity measurements in the high redshift universe. And this is a way to probe galaxy growth, and in particular the gas flows governing galaxy growth at early times over cosmic history. A lot of my work I'm indebted to collaborators. Most of this will feature data from the Moss-Tyre Deep Evolution Field Survey, the MOSDEF team here, spread across several UC campuses. Of course, Alice Shapley at UCLA, my advisor, and several other people. We've had a really productive time with the data set, and there's a lot of stuff I'm not going to highlight from MOSDEF, so if you want to look up some other results, there's a lot of other information. I'll try to maybe touch on a few things when passing through. So with the talk today, there's a few questions that I would like to answer during this talk that I hope when you come at it, you will also have the answer to. One is just what insights can galaxy metallicity measurements yield? So that's just some pretty basic background. And then what is our current ability to determine metallicities of galaxies in the high redshift universe? So for me, high redshift is redshift of 1 to 3. Some people that's low, some people that's high, so take it for whatever it is. And what are the primary uncertainties associated with these metallicity measurements? How can we address the remaining uncertainties using observations? And then finally, in spite of these remaining uncertainties, what are we learning in the meantime about galaxy metallicities at high redshift? So if you come out of here with an answer to at least some of these questions, then I've done my job today. So we better get this out of the way at the beginning. When I say metallicity, if that is an unqualified term, I'm talking about the gas phase oxygen limits of the interstellar medium given by 12 plus log over h if it's on a plot axis. So I may talk about the stellar metallicity and other things, but if I just say the term metallicity, that's what it is for me as a galaxy evolution person who likes the IS. So, what about galaxy growth? What do we want to learn here? Well, the basic question of galaxy formation evolution is how do we go from, gas in the beginning of time to the organized population of galaxies we see in the present day. And of course, those galaxies must have formed from something. And the cycling of baryons into and out of galaxies is sort of the main process, the main driver of galaxy growth over time. And the basic parts of this process are accretion of gas from the IGM or the CGM, the intergalactic or circumgalactic medium, into the galaxy. You need fuel. What does that fuel do? It forms stars, builds up the content of the galaxy, also builds up the gaseous content of the galaxy in addition to the stellar content. And then you have feedback from various processes. It can be AGN and high mass galaxies. For the lower mass galaxies, we think this is mainly driven by star formation, supernova feedback that can drive gas out of a galaxy, it can inhibit star formation. You can get more things that I've not shown in the simplistic picture. So these outflows that can be driven by feedback can then be recycled and reaccreted onto the galaxy. And this is the basic baryon cycling process that we think governs galaxy growth. Now there are a few key parameters that you would like to know to understand this picture. One is the star formation rate, so the rate at which a galaxy is forming stars. The integral of this is just the stellar mass of the galaxy. So if you know this over time, that's useful. The mass accretion rate, so this is the rate at which mass is being accreted onto the galaxy from the IGM and CGM. Then the mass outflow rate, which is sometimes parameterized as what's called the mass loading factor, which is just the mass outflow rate divided by the star formation rate. We would like to know these things to understand this process. So star formation rates, these are fairly easy to measure. We've measured these out to very high redshifts. You can use the ultraviolet, the infrared, a combination of these things. You can use emission lines like H alpha, and this is just an example of measuring this over a range of redshifts. We have a pretty good feel on how star formation rate scales with galaxy properties. These other two are the hard things, though. So mass inflow rates, these are very difficult to measure. There are some observations in the local universe, some high velocity clouds around the Milky Way, things like this that we think might be gas clouds accreting onto galaxies. In the higher redshift universe, we see very metal poor Lyman limit systems that are perhaps signatures of pristine gas accreting onto galaxies. But even if you can observe and confirm that there's accreting gas, to turn this into a global mass inflow rate is virtually impossible. So we can't really get this from observations. And as far as mass outflow rates or mass loading factors are concerned, we can observe these and confirm that outflows happen fairly easily. Here's just an example here of some rest UV absorption lines. So this is gas around galaxies that are about a redshift of 3. You can see that these rest UV absorption lines are all blue shifted with respect to the systemic velocity of the galaxy. That's a signature of an outflow. You can see this in emission lines as well. But again, to turn these observations into a mass outflow rate, you have to go through a whole host of assumptions that introduces a lot of systematic uncertainties onto the property. So I don't know if I would really trust very much if someone reports a mass loading factor or a mass outflow rate, that's a very robust value. So since we can't get these values directly from observations of inflows and outflows, what do we do? And this is where the metallicities come in. This cycling of baryons, this process, the metallicity of the interstellar medium is sensitive to this process. So when you accrete metal core gas, either from the IGM or the CGM, it's going to lower the metallicity in the ISM. It's going to dilute the metals. Of course, star formation produces metals, so that raises it, and then outflows, especially if they're supernova driven, they are driven at the site of enrichment, so they tend to remove metals from the galaxies. So, and what we really want to measure here is the way that galaxy metallicity scales with global galaxy properties such as stellar mass. This is the mass metallicity relation that you may be familiar with. There are other relationships that are very interesting. There's a 3-dimensional relationship between stellar mass, star formation rate, and metallicity. This is sometimes called the fundamental metallicity relation. That's very interesting. And the shape and normalization of these relationships encodes information about the balance of mass inflow, mass outflow, and star formation. And when we have observations of these, we can compare to the predictions from simulations. These are some simulations from Ramil Dave, the Mufasa suite of simulations, and see how good the feedback prescriptions are that we're putting into our cosmological simulations and other numerical simulations, and in the end come out with an idea of how feedback works in a much more detailed manner. And of course, if you can measure these relations over a range of redshifts, then you can probe galaxy growth at multiple epochs in history. So that's really what we want to do here. That's the background, the motivation. So we know a lot of information about these scaling relations at Redshift Zero. Here's just an example of the mass metallicity relation. So metallicity on the y-axis, stellar mass on the x-axis. You can see metallicity increases with stellar mass. This is from Christy Tremonti's seminal paper on this topic. We can do this for many galaxies in the local universe. The shape of this thing has taught us a lot about feedback in galaxies. There's a steep power law at low mass that shows that feedback is efficient in low mass systems. And particularly the slope of this, this low mass power law probes the efficiency of galactic winds, the way that scales with stellar mass. So this can give us information about the feedback, whether it's energy driven or momentum driven, things like that. At the high masses, this asymptotes, and feedback becomes less efficient for a variety of reasons, one of which is just deeper gravitational potential wells. And so this all agrees with what is needed to reconcile other observations, such as the halo mass-stellar mass relation. We need efficient feedback at low masses to suppress star formation. That's what's going on here. At higher masses that aren't shown as much here, AGN might come into play, but I'm just dealing with star-forming galaxies here. So we like to extend things like this to high Z to understand what is going on with gap flows in the high redshift universe. So the data set I'll be using to probe this is from the Mossfire Deep Evolution Field Survey. This was a large 4-year program that had 48.5 nights on Keck telescope using Mossfire to obtain res frame optical spectra of galaxies at a redshift of 1 to 3. So Mossfire is a great instrument. It's very sensitive in the near infrared. It's multiplex, so we can observe about 20 to 30 galaxies at a time. And we get res frame optical if we look at these redshifts. So these galaxies are selected based on their res frame optical magnitudes. That equates to a roughly stellar mass limited sample. So that's the observed H band is where we make that cut for our targets. And all the galaxies we targeted were in Candles fields. So these are extragalactic fields that have a ton of multi-wavelength ancillary data. It's very useful for us to maximize the science impact of the spectra. And in selection 2, we selected a sample of galaxies that span a very large dynamic range in properties like stellar mass, go down to about 10 to the 9 in stellar mass, a large range of star formation rates, both above and below the main sequence, and SED shapes. So we get quiescent galaxies, a small number, I'm not going to deal with those today. We get AGN, we get star-forming galaxies, we get dusty galaxies, we have a wide variety of galaxies in the sample. So here's our redshift histogram here. We targeted 1,500 galaxies and we ended up measuring redshifts for about 1,300 of those. So you can see the redshift windows we looked at. There's one at about 1.5, one at about 2.5, and then one at about 3.5 that you see here. And the multiple redshift bins enable evolutionary studies within this sample as well, which is pretty useful. And we chose these 3 redshift ranges because this is where the near-infrared JH and K bands line up with your res frame optical lines. So redshift 1.5, we're in the YJ and H band. You can see oxygen 2, H beta, oxygen 3, 5007, H alpha, nitrogen 2, and then the sulfur 2 lines. At redshift 2, you get the same lines, but they fall in JHK instead. And then at redshift 3, we just get the O2, H beta, and oxygen 3, and the other lines are redshifted out of the bands that we can easily access from the ground. So that's a data set that we're working with. It's a very great data set. The advent of these multi-object near-infrared spectrographs have really expanded our ability to look at the rest optical of galaxies at these redshifts. And the rest optical is a really powerful part of the spectrum to look in for emission line diagnostics. So here's a slightly good-looking example of a galaxy, I can't lie, but so you see we have the oxygen 2 H beta, oxygen 3 lines, H alpha, nitrogen 2, and sulfur 2 here. So we can look at dust attenuation using the Balmer decrement, the H alpha to H beta ratio. We can look at a star formation rate based on H alpha as well as the photometry that we have available. We can look at the ionizing source of the gas in these galaxies. So these are the lines that are used in the BPT diagram, which you will see a lot of in this talk, so get ready. This can tell you the difference between a star-forming galaxy, AGN, if shocks are involved, potentially has that diagnostic capability. The electron density of the gas, which in H2 regions is a probe of the gas density. We have the sulfur 2 and the oxygen 2 doublets can tell you information about that. The ionization state of the gas. So if you compare a high ionization species like O3 to a low ionization species like O2, this can give you an idea of how highly ionized the gas is. And then finally, the chemical abundances, the metallicity, so the oxygen abundance. We can look at other things like the nitrogen to oxygen abundance, the nitrogen abundance, so things like this we can also get. And for that, you typically use whatever line ratios are available to you. So I'm not going to focus on most of these. There have been other MOSDEF papers on AGN, on the star-forming main sequence, on the attenuation curve of Redshift 2. I'd encourage you to check that out. They all start with the MOSDEF survey in the title, so they're easy to search on ADS if you want to find some of those. What I am going to focus on is our ability to measure chemical abundances, and in particular over H, which I call metallicity here. So to understand how we do this, we're going to start at Redshift Zero, actually. So the emission line ratios that a galaxy produces are not random, but they're determined by the physical properties of the gas in H2 regions within a galaxy, okay? So this diagram we have over here, this is the canonical BPT diagram, nitrogen 2 over H alpha on the bottom, and O3 over H beta on the vertical axis here. And this diagram has canonically been used to separate star-forming galaxies, which follow a narrow sequence on this side, from AGN, from things with actively accreting black holes, which follow a sequence that stretches up and to the right on this diagram. And as I said, the position is not random. It's determined by underlying physical properties. And this cartoon on the right-hand plot, so this is the same diagram, but this cartoon gives us an idea of the physical properties that are involved in determining the location of the galaxy on this diagram. So we have, of course, the gas phase metallicity, which tends to move you up along this sequence. The electron density, if you increase the electron density, this can move you up and to the right. We have chemical abundance patterns, such as the nitrogen to oxygen ratio. If you increase the nitrogen abundance, it's going to inflate the nitrogen 2 line, so you're going to move horizontally to the right. We have the ionizing spectrum, harder EUV ionizing spectrum here. So if you have a harder spectrum ionizing the gas, things tend to move up and to the right. This is why AGN occupy this region of the diagram, because they're ionized by very hard spectra. And then we have this thing called the ionization parameter, represented as Q here. And this is a very strange concept that is very difficult to interpret physically, but it basically represents how highly ionized the gas is, how much of the gas is in a high ionization state compared to a low ionization state. It has to do with both the ionizing source and the geometry of the gas around the ionizing source. And so kind of a hard thing to interpret. But basically, if we look at emission line ratio diagrams, we have two-dimensional diagrams like this, and we have a number of parameters that are determining where galaxies lie. And so the question is, why do star-forming galaxies follow this well-defined narrow sequence here? And the reason is because all or most of these underlying physical properties are correlated or anti-correlated with each other fairly tightly. So we can see this here. So the left-hand plot, this shows nebular metallicity on the y-axis and stellar metallicity on the x-axis. Stellar metallicity is a proxy for how hard the ionizing spectrum is. So you go to lower metallicity stars, you get hotter stars that have a harder spectrum ionizing the gas. You can see that these two things are correlated and fairly close to 1-to-1, okay? Here we have the ionization parameter as a function of nebular metallicity, measured for local H2 regions. These are anti-correlated fairly tightly. And then here we have the nitrogen to oxygen abundance ratio as a function of nebular metallicity, and these also show a well-defined relationship here. And all of these are measured for Redshift Zero H2 regions. So the fact that these narrow sequences, the narrow relationships between these parameters exist is the reason why star-forming galaxies follow narrow sequences in line ratio diagrams. And that's the whole reason why we can measure metallicities for galaxies. We use line ratios to measure metallicities. And we measure metallicities because, and this is a dirty little secret of the trade, most metallicity indicators, the line ratios we use to measure them, aren't actually sensitive to metallicity at all. They're sensitive to these other physical conditions, but they happen to be correlated with metallicity, and so that's how we get here. Things like N2 over H alpha, mostly dependent on the ionization parameter, a little bit on the nitrogen abundance. Things like O3 to N2, just a measure of the ionization parameter. Things like N2 to O2, a measure of the nitrogen to oxygen abundance. None of these are actually sensitive to over H, but they are sensitive to other things that correlate with over H. The one exception, I guess, is the R2-3 ratio, oxygen 3 plus oxygen 2 divided by H beta, which compares the emissivity of oxygen to hydrogen. That's actually sensitive to over H because it's set up in a similar way. But these are the most commonly used metallicity indicators, these top two. And in fact, they don't actually probe metallicity directly. So to get back to why this matters for the high redshift universe, if we look at a BPT diagram and we put some high redshift galaxies on here, galaxies of redshift 2.3 from the MOSDEF survey, they don't follow the same sequence that the star-forming galaxies in the redshift universe follow. So in the Redshift Zero universe, galaxies are down here, and then the Redshift 2 galaxies are offset either up or to the right, or some combination of those vectors. They're offset in this emission line space. And because the location is determined by these underlying physical properties, that means that at least some of these physical conditions of the gas are evolving with redshift. And if those evolve, then our ability to measure metallicities is also evolving. And so if we use the same metallicity calibrations that we use in Redshift Zero and apply to Redshift 2 galaxy, this calls into question whether or not we're actually measuring the metallicity correctly for that galaxy. So this is the question that we're dealing with. So we need to wade through the degeneracy between all these physical properties, and we need to understand which ones are evolving and by how much they're evolving as a function of the gas phase metallicity in order to measure metallicity for high redshift galaxies. Okay? So the ideal thing to do here would be to have an independent probe of each of these. and use that independent probe and just figure out what the values for things are. So we can do that a little bit. So the electron density actually has an independent probe, and that's these oxygen 2 and sulfur 2 doublets. You can see some examples from our spectra over here. The ratio of the red component to the blue component in these doublets is a measure of the electron density, which is then a direct measure, nearly direct measure of the gas density in H2 regions. So we can use a number of these doublets. We've got dozens of these things measured in the MOSDEF survey. We can take the doublet ratios, and it's just an atomic physics calculation, so this is something that we don't worry about evolving with Redshift. And what we find is that at Redshift Zero, galaxies tend to have, or the H2 regions tend to have electron densities around 25 to 50 per cubic centimeter. And this is a factor of 5 to 10 higher on average at Redshift 2. So that seems like a big change, an order of magnitude in density, but it turns out if we use some photoionization models, it turns out that the line ratios are relatively insensitive to this change in electron density. So while we can measure this independently, it turns out that it's not really a driver for the change. The evolution isn't very important for the line ratios. So we can actually get rid of electron density. It reduces some of our degeneracy in interpreting which of these properties is evolving. So now we're left with these other things, the ionization parameter, the ionizing spectrum, nitrogen to oxygen ratio. So what do we do here? And this is where a lot of work has been focused on in this area in recent years, in the past few years. A lot of papers focusing on this. So there's been a few physically motivated evolutionary scenarios to explain why these different properties might be changing. So why might the ionizing spectrum be changing with Redshift? So this is a scenario that was put out by Chuck Seidel. They have a data set called the Keck-Periodic Structure Survey, which is in some ways similar to the MOSDEF survey. And they find that they can explain a harder ionizing spectrum and fixed metallicity with Redshift due to having iron-poor stars at high redshift. And the idea here is that iron is the important element for determining the stellar spectrum. Okay? The iron abundance in a star tells you how much metal line blanketing you have in the UV and how many of your hard UV photons make it out of the star or not. And what happens here is that if you have a very young stellar population with an age less than, say, a gigayear, if you have a starburst, a gigayear after that starburst is when type 1a supernovae will happen, and that's where the majority of the iron comes from. Okay? So if you have a very young stellar population, then most of the iron from a starburst has not yet been produced, but the oxygen comes from type 2 supernovae, so it's already been produced. So you have more oxygen than you would expect compared to your iron if you were to use, say, a solar abundance pattern. And so what this means is that at fixed nebular metallicity, you have much harder ionizing spectra at high redshift where galaxies can be that young. At Redshift Zero, galaxies really aren't that young. They'd be extremely rare to have a galaxy that young. So that's one possible explanation if the majority of these galaxies at Redshift 2 and 3 have very young stellar populations, less than a gigayear. Another option would be to modulate the nitrogen to oxygen. You can do this by using gas flows. So if you, again, you form a lot of stars, you produce a lot of oxygen. Turns out nitrogen does not come from type 2 supernovae. It comes from intermediate mass stars, and it's not produced until 200 or 300 million years after the starburst. And so you wait a few hundred million years, you produce the nitrogen, you have some nitrogen to oxygen, but then you accrete a lot more hydrogen for a new star formation epoch. And this decreases over H while keeping N over O fixed. And so then you have a higher nitrogen to oxygen ratio than you would expect given your metallicity here. So that will mess up all of your line ratios with nitrogen. And then finally, the ionization parameter. Some people have proposed that the ionization parameter might be higher at fixed metallicity at high redshift because star formation is more concentrated in high redshift galaxies. Although to be honest, I'll tell you that I don't understand the physical argument for this mechanism, so I don't think that this one is as likely as something going on with the ionizing spectrum or with the nitrogen to oxygen abundance, which seems to have a more sound physically motivated model here. So in reality, of course, it might not be only one of these things, it could be a combination of these things. So that's what we're dealing with. So what we want to do is just take an empirical look at this with the MOSDEF data and see what the data are telling us and see if we can get a better handle on what's going on here because we're working with a lot of degeneracy between these properties. So I'm just showing here line ratio as a function of stellar mass. This is O3 over H beta as a function of stellar mass. In blue, we have a Redshift 2 sample. In red, we have a Redshift 3 sample from MOSDEF. The stars here are stacks in bins of stellar mass, just so you can see the average sequences, and then I'm just comparing the average sequences over on this side. So a very clear result is that at high redshift, galaxies have much higher excitation. So galaxies in Redshift 2 and 3, much higher excitation than Redshift 0 galaxies at fixed stellar mass. You can see that by the very high elevated O3 over H beta ratios here. Now the question is, how much of that elevated excitation is just due to the lower metallicities that these galaxies have, and how much of it is due to the evolution of these other parameters? That's what we like to get at. And so with MOSDEF, since we have all of these line ratios available, we can use multiple line ratio plots simultaneously to try to tease out the details here. So what I'm showing here is, this is again the N2 BPT diagram. This is the sulfur 2 BPT diagram. So O3 over H beta is a function of sulfur 2 over H alpha. And this is a Redshift 2.3 sample for MOSDEF. And you can see that it's offset from the Redshift 0 sample shown here. And this is just a median line for the Redshift 2 galaxies. And I've divided the sample up into a large offset in the N2 BPT and a smaller offset in the N2 BPT. Okay, so the blue is the large offset, red is the small offset. If we look at these galaxies in the sulfur 2 BPT diagram, we see that A, the Redshift 2 population is not systematically offset at all from the Redshift 0 galaxies in this diagram. And then B, the galaxies that were highly offset in the nitrogen 2 diagram are actually mixed in the sulfur 2 diagram. The two populations of galaxies are not obviously different in the sulfur 2 diagram. So this suggests two things. One, since this offset is in nitrogen and there's not an offset in sulfur, this may suggest that you should call into question the nitrogen abundance, and that we should perhaps think that there's an evolving nitrogen to oxygen ratio. Secondly, if there was a harder ionizing spectrum, it would drive an offset in both of these diagrams. So if the galaxies were offset up and to the right in both diagrams compared to Redshift 0, that would tell you that there's a harder ionizing spectrum. We don't see an offset in this diagram. And so we took this to mean that there's not a harder ionizing spectrum with Redshift, but that there is perhaps an evolving nitrogen abundance with Redshift at fixed metallicity. But it turns out that in this diagram, and particularly in the sulfur diagram, there's a really subtle argument that calls into question what we've done here. And it's not an issue with the high redshift stuff, it's actually an issue with the Redshift 0 galaxies. And it's a pretty big issue. So it turns out that Redshift 0 galaxies, they have H2 regions, but they're a lot more than just H2 regions, as we know. And in fact, about half of the line emission from Redshift 0 star-forming galaxies doesn't come from H2 regions. It comes from diffuse ionized gas that exists outside of H2 regions. This is just a narrowband image where H2 regions have been removed. You can see there's a huge amount of H alpha emission that does not come from H2 regions. And the problem here is that the dig gas has a different set of physical properties from H2 regions, and so it has completely different line ratios than H2 regions. And so if you include this in your spectrum and then you try to measure metallicity, you're going to get the wrong answer, because the metallicity calibrations are based on H2 regions, not on stuff with diffuse gas. You can see this very clearly in these plots here. So this is again the nitrogen 2 and the sulfur 2 BPT diagram. And I plotted the Redshift 0 Sloan galaxies in the gray. The red points are individual H2 regions from Redshift 0. And then the blue lines are measurements of diffuse ionized gas at Redshift 0. And what you can see here is that in the N2 BBT diagram, everything lies on top of each other, so that's fine. You're not actually biasing yourself in that diagram. In the sulfur diagram, H2 regions lie over here on the left, and DIG lies over here on the right at very high sulfur 2 to H alpha, and the Sloan galaxies lie midway between these two. So as you might expect, galaxy spectra are a mixture of H2 and diffuse gas. The problem here is that what should we think about high redshift galaxies when it comes to this diffuse gas? And on this right-hand plot, I'm showing the fraction of H alpha emission coming from the diffuse gas as a function of H alpha surface brightness. So starburst galaxies live over here, and relatively quiescent galaxies live over on this side. And we see that the importance of DIG decreases as the concentration of star formation increases. So starbursts over here this is what your high redshift galaxy is going to look like. Very highly star forming in a very compact galaxy. Okay, so the expectation, if this trend holds up to high redshift, is that dig is negligible at high redshift. So we shouldn't be comparing high redshift galaxies to SDSS galaxies or integrated galaxy spectra. It would be a more fair comparison to compare them to individual H2 regions. So this changes the whole story in some of these emission line ratio diagrams. So now the comparison is not between the gray cloud and the blue and red points. It's between the H2 region sequence, which would be somewhere over here, and the blue and red points. And now we can see there is clearly an offset between those two things. So we need to revisit a lot of the conclusions that were drawn comparing Redshift Zero galaxy spectra to high redshift galaxy spectra based on the fact that this diffuse emission is very important. So this tells us that there probably actually is a harder ionizing spectrum that we have to deal with, but there still may be some N over O evolution as well. Now, one other thing we can do is just look at an empirical, completely empirical view of the line ratios that are sensitive to metallicity as a function of stellar mass. Okay, so each of these plots is a different line ratio: N2 over H alpha, O3 over O2, N2 over O2, and then O3 over N2. These are each used as metallicity indicators. I've just plotted them as a function of stellar mass. We have the Redshift 2 galaxies in blue with stacks in black, and then the green points are Redshift 0 galaxies. Okay. And these Redshift 0 galaxies have actually been corrected for the diffuse gas emission, so we don't have to worry about that bias in this plot. What we see here, we see a few things. We see that these metallicity-sensitive line ratios very strongly correlate with stellar mass. Theory expects that metallicity very strongly correlates with stellar mass. With increasing stellar mass, we find a lower ionization parameter. You can see that as O32 decreases, O32 decreases, and higher nitrogen abundances. You can see that in the N2 and the N2 over O2. And all of this is as expected if metallicity correlates with stellar mass. These are the same trends you see at Redshift 0. They're driven primarily by metallicity at Redshift 0. And what's more, actually the slope of these relationships very well matches, in most cases, the low mass slope of the Redshift 0 galaxy distribution. So I'd argue that empirically, we have good reason to believe that strong line ratios are still a very good indicator of metallicity at high redshift. Even though there is some evolution in these physical properties that affect the metallicity calibrations, they still are a good measure of metallicity at high redshift, and that perhaps the biases are not as large as one might assume if one doesn't have an empirical view like this to take. So, but going back to this, I mean, we still need to deal with this stuff to get really accurate metallicity measurements. So is there a solution here? You know, we have these degeneracies that are very hard to break. Is there a solution, something that we can do to figure this problem out? I would argue that there is. And a path forward here is actually an observational path forward. And what we can use are these very faint emission lines called auroral emission lines. And these particular emission lines are sensitive to the temperature of the ionized gas. And of course, if you put more metals in a gas, it's going to be more efficient at cooling. So a metal-rich gas is going to have a low equilibrium temperature. Less metals, higher equilibrium temperature. So the temperature of the gas is a measure of the metallicity of the gas. So if we can measure these weak auroral lines, such as oxygen 340-363, you compare this to one of the strong lines, like O3 5007, this gives you the electron temperature. Combine this with some hydrogen Balmer lines, and you can measure an oxygen abundance. And this is an atomic physics calculation, so this does not have any bias. This should not evolve with redshift, okay? And if you have some number of these, you can reevaluate the applicability of these metallicity calibrations at high redshift, even recalibrate if you need to. But the problem is these auroral lines are about 100 times weaker than the strong lines we typically measure in a high redshift galaxy spectrum. It can be done in the high redshift universe. I wouldn't be telling you about it if the answer was no. So here are 4 measurements of this line from the MOSDEF survey. Some of them are fairly low significance, like this right here. These 2D spectra don't look fantastic on this projector. But these do appear to be real measurements of this O34363 line at redshift greater than 2. I'll just let you know, up until 2 years ago, there were 0 measurements of this line above redshift of 2. So this is really groundbreaking. And the idea here, I'm just going to highlight one galaxy at redshift 3.1 for which we had this measurement. You can see the spectrum here. The types of galaxies we can measure this for are not typical galaxies. They're these extreme emission line galaxies. They have massive equivalent widths in the oxygen 3 5007. They're very high excitation, high ionization state, very highly star-forming, fairly low metallicity galaxies. And what we would like to do is take the electron temperature-based metallicities. So the x-axis on all these is metallicity based on the electron temperature. We take high redshift points, like this redshift 3 point, which is the red star. I also have some redshift 1.5 points in these other colored points. The blue points here are from redshift 0.8, and then the gray dots are from redshift 0 galaxies. And so we'd like to compare this as a function of redshift and see, at fixed metallicity based on electron temperature, do the emission line ratios evolve with redshift? And the answer to that may be yes, it may be no. But if we get a statistical sample of these things, we can evaluate how large the evolution is, and then we can robustly determine metallicities based on the revisions to the metallicity calibrations we can make with this. So I think this is a really promising step forward. So the current and future status of using these auroral emission lines to measure electron temperatures, right now there's a handful at redshift 1 and 2. There's only one published at redshift greater than 2. There's no other auroral lines. There's auroral lines for other species like oxygen 2, nitrogen 2. There's none of those detected at redshift greater than 1. So what can we do to make progress? Well, the real hindrance to the progress is that this is a very faint line. So if we want to detect it, we need to target very high specific star formation rate, low metallicity galaxies. The other thing that hinders progress is that there's only narrow redshift windows in which you can get these lines from the ground. There's a list of the redshift windows right here. And surveys that have targeted high redshift galaxies have not been focusing on these redshift windows. So with a targeted survey looking for the particular types of galaxies that you can measure this line for right now, in the next couple of years, we could get a sample of 10 to 20 of these galaxies with ground-based facilities, okay? And this would be really revolutionary because right now, again, there's only one published measurement at redshift greater than 2. So we could start to evaluate real robust nebular metallicities at high redshift. And then by the time James Webb arrives, this will become much more commonplace. We can get this for tens or possibly even hundreds of galaxies with James Webb for a range of species. And so James Webb will be very revolutionary, but in the next couple of years, we can do a lot of groundwork to really maximize our ability to use James Webb. James Webb will be able to do this for more typical representative galaxies. So I think there's a very bright future here for this. It will be an observational investment, but it is possible. So that's sort of the current state of our ability to measure metallicities. There is this inherent systematic uncertainty. We don't yet have the observations to completely eliminate it. But we can learn things in the meantime. And so I'd like to finish up just showing some results about some of these metallicity scaling relations and what it's teaching us about the gas flows in galaxies at high redshift. So one of the relationships I mentioned at the beginning is this 3D relationship between stellar mass, star formation rate, and gas phase metallicity. This is just a plot of this relationship at redshift 0. So we have, so the way this is metallicity on the y-axis, stellar mass here, and this is color-coded by star formation rate, where low star formation rate is red, high star formation rate is purple. So at fixed stellar mass, you can see highly star-forming galaxies have lower metallicities. And this is a very sensitive probe of gas inflows and outflows, and it's a very real depiction of the cycle of baryons in these galaxies. So the way this relationship is interpreted is that if a galaxy has a large gas inflow, that's going to drive a lot of additional star formation, so it's going to pump up the star formation rate. And when you accrete all that gas for a gas inflow, it's also going to lower the metallicity. And so you get this relationship right here. So this is a very tangible way to measure the cycle of baryons. And the form of this is a very sensitive probe of how the feedback is working and the metallicity of the gas that you're creating a lot of these very fundamental values. So this relationship is predicted to exist at high redshift by pretty much every chemical evolution or cosmological simulation that you can use. So it's very strongly predicted by theory, but it has not yet been observationally confirmed at high redshift. So it's sorely needed. If it's not there, then our basic view of how galaxies grow over time is not correct. So definitely something we'd like to confirm. And there was another prediction. So this paper by Filippo and Nucci that discovered this relationship at redshift 0. Basically, they made a prediction that high redshift galaxies lie on the exact same MSZ relation as redshift 0 galaxies, and they call this the fundamental metallicity relation. And so high redshift galaxies have lower metallicities corresponding to their higher star formation rates at fixed stellar mass. So that's another thing that we like to test, whether or not this empirical prediction by Minucci holds at high redshift. So there are two questions to answer. One, does this relationship exist in the high redshift universe? And then two, do high redshift galaxies follow the same relation as Redshift Zero galaxies? In other words, does this fundamental Metallicity relation hold? There's been a lot of literature discussing this. People have said both yes and no to this question, myself included. But all the previous studies have had small samples. They've often mixed different metallicity and star formation rate estimators, non-uniform sample selection. There's a lot of issues, and with the MOSDEF sample in its full form now, we can overcome all of these and do consistent uniform analysis from Redshift 0 to Redshift 2 to investigate these questions. So first, what signature are we going to look for the MSZ relation? So you can look for correlated scatter around the star formation rate as a function of stellar mass and the metallicity as a function of stellar mass. So you have a relationship like this. If you take the residuals in star formation rate and plot them against the residuals in metallicity, you should see an anti-correlation between those two residuals. This is again a prediction from simulations of this relationship. So what we're going to do is I'm going to look at the residuals around the star formation rate as a function of stellar mass and the metallicity as a function of stellar mass in Redshift 2 and see if we can find this anti-correlation. So here, this is specific star formation rate as a function of stellar mass. So we're going to take the residuals around this mean relationship shown by the red dashed line. And then over here, the mass metallicity relation. This is using the O3 over N2 line ratio to measure metallicities. So we're going to take the residuals around this and then plot those against each other and see if we can find this anti-correlation. And indeed, we find this, not just for O3 N2, but also for a host of other metallicity indicators. There are more that I didn't put on this slide because we don't need that many plots. So we find this anti-correlation. It's statistically significant in all cases. We also see it in stacks, shown by the colored stars here. So stacks in star formation rate and stellar mass. We see this anti-correlation. So this is not just showing up because of our observational limits. This is actually truly in the data. So the slopes differ slightly based on the metallicity indicator that they use, but they're generally consistent. So our average slope down here is minus 0.13, just a unit slope, I guess, in this case. So if we compare that to the predictions from these cosmological simulations, they're actually fairly close, okay? Now keep in mind that this still has some systematic uncertainty because we don't exactly know what's going on with the metallicity calibrations at high redshift. But we're doing pretty well. So if this is fairly robust and not extremely biased, then our current feedback prescriptions in these cosmological simulations are doing a good job of predicting these metallicity scaling relations. So that answers the first question. We've confirmed the existence of this 3D relation between these properties in the high redshift universe.
Sure.
So that's good.
I have to
Oh yeah.
stop.
Sure.
So when you're looking at these, I know it's hard to do these measurements, but you see that there's substantial scatter, especially in the middle bond, right?
Yeah.
And you could argue that there are potential biases, and if you look at the range in a specific star formation rate, you're really only measuring over an order of magnitude.
Mm-hmm.
And there's, I understand that there is scatter predicted from the simulations as well, but I'm always just a little concerned that, you add or subtract a couple of points and you get a very different slope.
Yeah, so I would say that our ability to reproduce this very faithfully in stacks, where we include not only the things here, but all of our limits, somewhat would do something to allay those fears, I think. It is a little tricky, but the other thing is that so we see this in 4 or 5 different line ratios simultaneously, and each of them has different systematic dependencies on the uncertainties that you're referring to, okay? And so for it to actually produce this in all of the plots simultaneously, like if all of these anti-correlations were fake, that would take a very contrived combination of the associated uncertainties to reproduce this in all the line ratios simultaneously. So I think that's one strength that we have here.
Right, so did you try just doing like really basic stuff, like just mixing up all the measurements and see if you recovered in meaningful relationships, even if you use, randomized?
Yeah. So if you do that, then you don't on average recover statistically significant correlations.
Yeah, so on average you don't recover, but you do.
Right.
Even when the data are junked, you still recover relationships.
No, not on average. No.
I know, not on average, but
A very small percentage of the time.
right.
But
so
then
is it 2 sigma or 1 sigma percentage of the time?
I don't know off the top of my head. The problem is that when you do that, when you randomize it, the chance that you would do this in 5 line ratios simultaneously is extremely minuscule. If you were talking just the N2 over H alpha measurements, how often could I like recover this from noise? That's fine, but to do it in 5,
So,
not all of them are independent, but
Right.
there's some level of independence there. So,
Yeah,
yeah.
it's just a grain of salt, that's all.
Yeah, sure.
Yeah, let me turn your volume up, sorry. Okay, yeah, you talk.
No, that's it. Yeah, no, I think that's a good point. There's one question I had for Ryan on this as well. Well, it's two. One is, when you said this then matches the predictions from simulations quite nicely, that must be over kind of a limited, or whatever the mass range is, whatever which you're comparing it. I'm just thinking in terms of stellar mass. What range is that? I mean, if you're talking about like matching simulations, clearly the feedback efficiency is going to change depending on the mass.
Right,
and
so.
it's only impacted over a certain mass range.
Yeah, totally. So this is about 10 to the 9 to 10 to the 11 is the range over which we have a pretty good level of recovery for MOSDEF.
Okay, so take away is that actually matches pretty well with the simulations in that mass range.
Yes, yeah. No, that's totally true. That's a great point. In fact, this relationship between the stellar mass star formation rate and metallicity at Redshift Zero, it is strongly mass dependent, and you see in the very massive galaxies of Redshift Zero that this relationship actually goes away. The star formation rate dependence goes away at high masses at Redshift Zero. So that's something that it would be great to investigate as a function of stellar mass, but right now, I mean, you can see the scattered view is pointing out, we don't have the statistics to be able to do those more detailed, as a function of stellar mass comparisons right now.
Yeah, sure, that is a great explanation. In fact, that was my next question is, what can you do with a mass event? I have one more question about, sorry, I'm just thinking about these questions about bias here. Are you biased in any way toward galaxies with lower specific star formation rates? I mean, should we worry about that at all? I was trying to decide in my head if that's true or not. I mean,
Oh,
if there are fixed stellar
yeah,
masses
so one thing I can show you.
Would you be as sensitive to detect the line emission from the galaxy or in the stacks? Is that all good?
Yeah, so one thing I can show you here, so here on the specific star formation rate as a function of stellar mass, it's probably really hard to see for you through the computer. But this line here is our star formation rate limit based on our depth for our emission lines, okay? So basically above 10 to the 9.5, we are complete in specific star formation rate, okay? We're not bumping up against the detection limit above 10 to the 9.5. So on the very lowest stellar mass bin, yes. But basically, 4 out of 6 of these bins are at specific star formation rates where we actually are complete down to the line flux that we're sensitive to. So I think we're doing a pretty good job there. But yeah, that is a worry. Yeah.
That's cool. Yeah. Thanks.
I mean, it's very brave that you're doing that. I just,
Yeah, no, I mean, these are great things to think about. So I'd just like to finish up answering the second question about this relationship, okay? The second question is, do the high redshift galaxies lie on the same relationship as the Redshift Zero galaxies? So if I choose a stellar mass and a star formation rate, will high redshift and low redshift galaxies have the same metallicity if I fix those things, okay? So what we're doing here, this is again, stellar mass on the x-axis, metallicity is a function, or based on different emission line ratios on the y-axis. So we try to perform this with as many line ratios as we can, these investigations. These squares are Redshift Zero galaxies from Sloan. They're bin in stellar mass and star formation rate, okay? You can see the color coding for star formation rate here. And then the stars are the Redshift 2 sample, and they are color coded in the same way for star formation rate. And the really important thing about this comparison is that the stellar masses are essentially equivalent. The star formation rates are all from H alpha dust corrected, so they should be as fair of a comparison as you can make to Redshift Zero. And the metallicities are based on the same line ratios for the samples. So it's as direct of a comparison that we can make. And what we see is that at fixed stellar mass and star formation rate, the high redshift galaxies, so if you match in color basically, the high redshift galaxies tend to have lower metallicities than the Redshift Zero galaxies when you fix those properties. Now you might come and say, well, hey Ryan, you just told me about how there's this systematic difference between the Redshift Zero and the Redshift 2. So like, is this offset that you're seeing just a result of those evolving physical parameters, and it might not actually be real? And this is where, again, performing this with a bunch of line ratios simultaneously helps us out, because the systematic effects from those different evolutionary scenarios would not reproduce this offset in all the line ratios simultaneously. So let's say your N over O was changing. Well, that might reproduce this, but it could not reproduce this one that's only dependent on the ionization parameter. And so you can make arguments like that to say that qualitatively this offset towards lower metallicity is there, even if qualitatively the exact value is affected by the systematics. Okay? So we appear to have this robust result that at fixed stellar mass and star formation rate, the high redshift galaxies have lower metallicities. So, well, that's the uncertainty that I was talking about. So how do we interpret this? What does this imply? What do we actually learn from the fact that they have a lower metallicity at fixed mass and star formation rate? So we can go to some chemical evolution models. There's a couple of leading models here. And we can look at these chemical evolution models and say what parameters need to change in order to reproduce this offset that we observe between Redshift 0 and Redshift 2. So one option is if at higher redshift at fixed stellar mass, we have lower star formation efficiency. So basically the star formation rate per unit gas mass decreases with redshift. This is probably wrong, because all of the cold gas observations we have at high redshift suggest, if anything, high redshift galaxies have a higher star formation efficiency. Okay? So we're going to rule that one out. Doesn't seem like it's plausible based on the observations. Another option is if you have a higher mass loading factor, so this mass outflow rate divided by the star formation rate, if that increases with redshift at fixed stellar mass, then you can reproduce this offset based on the chemical evolution models. This is generally in agreement with observations, but the constraints are really poor, so we'll say that's a possibility. And the final possibility is that you have a lower metallicity of the infalling gas. So the gas that's being accreted onto a galaxy is lower metallicity at high redshift than low redshift. This might seem extremely intuitive, but it's actually telling us something kind of cool and concrete. So if again we go to some simulations, so these are from the fire simulations, and this is a snapshot of how many is this? 6 galaxies at redshift 0, and the same 6 galaxies at redshift 2. The y-axis is the fraction of the stellar mass that was formed from different sources of gas or stars. And I want you to focus on the purple stuff, which is accretion from the IgM, so this is pristine gas accretion, and then the blue stuff is recycled gas from outflows. So stuff that was blown out of the galaxy, it's enriched in metals, and it gets recycled back into the interstellar medium. And basically what you can see is at redshift 0 in the simulations, the pristine gas component is a smaller component of the stellar mass formation compared to at redshift 2, where the pristine gas component is actually a very large component in comparison to the recycled gas and the other sources. And so what we think is going on here is that there's a lower metallicity of the infalling gas at high redshift because accretion of pristine gas from the IgM was relatively more important at high redshift, whereas recycling of winds was relatively less important. At redshift 0, the script actually flips, and recycled winds and actually even a transfer of metals between neighboring galaxies from winds is actually the dominant source of gas in redshift 0 according to numerical simulations. So that's what I think we're learning. So I'll put up my conclusions here. I hope I did a relatively good job of answering those questions I posed at the beginning. So these metallicity scaling relations can tell us a lot about the way the galaxies grow and the gas flows here. But there's a lot of uncertainties regarding these evolution of these physical properties that determine the emission line ratios, and this results in systematic uncertainties in the metallicities at high redshift. One way to approach this problem is to get measurements of these temperature-sensitive auroral lines at high redshift, and we're starting to do that, and we're going to take a more targeted observational campaign to target specifically the types of galaxies we can get that measurement for in the future, preparing for James Webb, which will allow us to do this for more representative samples. And then finally, in the meantime, we can still make qualitative inferences about the evolution of the metallicity. And in particular, what I showed here suggests that potentially there's evolution in the mass loading factor of the winds, but in particular, we seem to come to this conclusion that the accretion of pristine gas from the IgM was more important than wind recycling in the high redshift universe. So I'll go ahead and leave it there. Thanks for paying attention, and I'll take any questions. This one?
So yeah, so like the purple,
Yeah.
so that's like fresh accretion, you say. So accretion can either mean like mergers or smooth accretion in the context of these things. Like those purple like doesn't distinguish between those two things. Is that correct? Or
Yeah. So I didn't go into detail on all the colors. So the red stuff is dry mergers, and the orange stuff is gas-rich mergers. Yeah. So this purple stuff is supposed to be, they basically trace the particles.
oh, okay. So the purple stuff is actually,
Originated from the IGM, came
particles
through
coming
the,
in.
came through the Virial radius.
And the red is the red are like mergers of smaller systems.
Yeah.
The red is that.
Yeah.
Okay. So mergers are, does that say they're more important than hydrogen?
I think they just might have had one weird system.
Okay.
Because the way, fire was like a zoom in on a few systems, and so they might have just gotten one weird cosmic variance issue there.
Okay. How many halos is that?
Sorry?
Is that how many halos is this looking at?
Oh, so these are each just individual systems.
So there's like one of you. Okay.
Yeah, there's 6, and they span some range in halo mass here, from low mass to high mass, and at 2 redshift snapshots. Yeah, that's what they did in this paper. So it's not a ton of systems, but to do the detail that they do in the hydro, they're limited.
I'm surprised there's still significant fresh accretion even in Redshift Zero
Yeah.
for all of those systems.
Yeah, I mean, the other thing is that this has to be integrated over some sort of
Sure.
time length, and so I'm actually not sure how they
I was
bring
in
that. Yeah.
a couple of years or
Yeah,
something.
I mean, one really interesting thing is this green part gets really big at low redshift, and that's actually intergalactic transfer of
That's
material.
CGM. Is that what you would argue as being CGM?
That does go through the CGM. So the blue stuff is stuff that the galaxy blew out and it reaccreted. The green stuff is stuff that the next door halo blew out, and it escaped that halo and went into that halo and got accreted onto that galaxy. Which is an interesting part, but both the blue and the green are going to be pre-enriched because they came out of a galaxy. They were blown out by feedback. And so that's the important, is that the blue and green stuff is metal rich, the purple stuff is metal poor because it came from the IGM. Yeah.
So I'm going to ask you, obviously, Ron didn't ask the question, which is, given the large scatter in your measurement, would it be better to have fewer measurements but with higher signal noise and thus smaller error bars? Or would it be better, and you can't have both,
Yeah.
or is it better to have more measurements with comparable error bars?
So I think for what I'm trying to do, I prefer more measurements with comparable error bars because this is really like a population study, right? And so you want to get a good average of the population. And so even with a large number with worse error bars, you can stack, you can bin things, and you can get a good idea of the average if you treat your biases in the stacking process properly. With a small number, even if they're really precise, we might worry that we're not getting a good average of the population. That might, throw us off in the wrong direction. That's a good question. I mean, in some sense,
Because you're battling a bunch of biases, observational in terms of even being able to sample certain regions.
right?
So it's just, how do you
Yeah, it's
how do
tough.
you tighten that up?
I mean, potentially if you did have a small number of very high signal noise measurements, that can help you assess the biases on your larger sample with poor signal to noise, right? So, but I can't have both.
You can.
You said I can't have both, so I guess I can't do that. Yeah, that's a good question. I mean, at least with the numbers we have here, hundreds, you can get a stack and you can get a pretty good error bar on a stack.
Yeah, but like I said, I understand this is still really nice work. And the concern I always have is the average of the average is not the same thing as the average of the whole, right? And so
Right.
when you start, I play this game too.
Right, yeah.
Because that's all you can do.
Yeah.
But this is always something that's sort of in the back of my head.
Yeah, so I will say, I agree with you, stacking, binning, these all carry their dangers. One thing we've been able to do with MOSDEP is take I guess, a high-quality sample. We have a subset that has all the lines we're using detected, and I stacked them all in a myriad of ways and figured out which way gives you the least systematic bias across those things.
Yeah, that's really good stuff.
Yeah, so we can do that. The other thing I've been trying to do is, under assumption for different priors for the distribution functions of the galaxy properties, see how big the biases in the stacks that we include the limits are, given that we don't exactly know the prior distribution of the limit population. And when you do that, you can at least give a level for how much you may or may not trust it based on some perhaps reasonable assumptions. So, but in the end, you don't know.
You would do that. Any last questions?
Can I ask
Yes.
something?
Yeah, sure, let me turn your volume up a little bit.
Yeah, I have my hand up when my video's off because I was. It's okay. Yeah, no, it's a really nice talk, really great work.
Thanks.
So I wanted, the one thing I actually intrigued by your comments that nitrogen to oxygen abundance ratio may evolve with Redshift, which is probably predicted just because it is nitrogen, I believe, so is understood to mostly come from the CNO cycle. So you probably expect some of that. Is it actually in the direction I think then that it's going down as I go to higher redshift, or the nitrogen to oxygen abundance is lower than as I go to higher redshifts?
Yeah, so the particular prediction for the evolution is not just that the nitrogen to oxygen would be lower at fixed stellar mass or something like that, but actually at fixed metallicity. And so the correlation is that nitrogen to oxygen increases with increasing oxygen abundance. That's what we see at low redshift. And so we would say if that evolves, then the high redshift galaxies don't lie on the same relation between those things. And so they may have lower overall nitrogen to oxygen abundances, but if you look at fixed metallicity, they may have higher than you would expect. And it's the metallicity that factors into how much nitrogen comes out of the CNO in those intermediate mass stars. So that's the tricky part, is all of this needs to be done at fixed metallicity, but we aren't super confident in our ability to measure metallicity at the moment, so that's like the problem. That's why I think these temperature sensitive measurements, we can get those, we get the metallicity independently, and we don't have to worry about all of these other issues. So
Yeah, that makes a lot of sense. Exciting, thanks. I have one more question about the diffuse interstellar gas, which was starting to intrigue me during your talk. So, would you expect then, if you somehow tried to divide up your sample as a function of size, would you see differences? Just thinking if, a galaxy has, if take two galaxies, fixed star formation rate, one is much more extended than the other, would you see the effects of this diffuse interstellar gas more? And does that actually mean we have to worry about structural or size dependent differences when we're doing all these various ionization measurements?
right, yeah, so that, yeah, totally. So for Redshift Zero, you absolutely have to worry about this. I had a paper that I didn't really put the results in here, but we modeled the Sloan galaxies as a mixture of H2 and dig and provided correction functions to remove the dig based on the H alpha surface brightness of the galaxy that you're looking at.
Nice.
But basically, our high redshift sample all lies in the regime where the dig would be negligible if it follows the same dependence that the local galaxies have on the H alpha surface brightness. But we don't actually know at high redshift, right? Even though the galaxies are more compact, there's a lot of star radiation, there's also a lot more gas, and so potentially there could be a diffuse component that's comparable to the H2 regions. The only way to figure that out is with spatially resolved observations. So we are in the process of following up some bright MOSDEF targets with OSIRIS on Keck to get spatially resolved line maps with adaptive optics. And so in those, we actually can check, do the line ratios systematically shift towards dig line ratios when we go to low surface brightness regions? And that can tell you if the dig is actually existing in a form you have to worry about at high redshift or not. So yeah, I think the spatially resolved observations are the best way to try to figure out that problem at high redshift.
Yeah, that's cool.
Okay. So we'll let Ryan get to lunch. So thank you again for very knowledgeable.